Hello, everyone. Thank you for being here. My name is Yuval. I'm Chief Commercial Officer of Quera Computing. So Quera, born at Harvard and MIT. We're based in Boston, although we now have offices in Japan and the UK. We're advancing together to this day. Harvard and MIT are really part of our secret sauce. The reason we're so advanced, the reason we're so far ahead of everyone else is that our close collaboration with Harvard and MIT. We believe, and I'll show you, that we are both the scientific and commercial leader in quantum computing, and specifically in neutral atom quantum computing. We have systems available worldwide. Our first system is soon celebrating its third birthday on AWS Bracket, 256 qubits. Well-funded, $230 million, most recently from Google and SoftBank, and just last week it was announced that NVIDIA decided to join the party, and we're happy to have them. And as I mentioned, also offices in Japan with one of our systems, and in the UK as part of the National Quantum Program. Why neutral atoms? Well, neutral atoms are, as the previous speaker said, we use rubidium and we like it very much, right? The reason to use neutral atoms is as follows. First, it's a natural qubit. It's not a manufactured qubit, which means that we can take a million qubits, a million atoms, and they would be perfectly identical. No manufacturing defects, no inconsistencies, no production delays, as many as you want. The other thing is that they work at room temperature. And so when we go to high-performance computing centers and say, oh yeah, we have the small system, it works at room temperature, it needs 10 kilowatts or 20 kilowatts of power, they say, kilowatts? We don't understand that word, K. We know what megawatts is. So, oh no, it's 0.01 megawatts. That's what you should really know. Room temperature operation, no cryocooling, very, very simple. The other thing is that we trap these atoms, these qubits, using lasers. It's almost like these movies that you saw where there's a bank safe and the laser beams coming from the ceiling and the villain tries to evade them. So we use these laser beams, those tiny ones, to trap the atoms and move them around. And when we can move the atoms, that means we have what's called all-to-all connectivity, which means that every qubit can connect with any other qubit. So if I'm a qubit and I want to speak with Scott at the other side of the room, I would just go and speak with Scott. But if I'm a superconducting qubit and I can only speak with you and I ask you to pass the message to him, and so on and so on and so on, and eventually to Michael over there, and then 3 steps later we'll get to Scott. By the time it gets to Scott, who knows what the message will be. So this ability to shuttle qubits around, to move them, to have any qubit connect with any other qubit is really fundamental to having efficient algorithms, to having error correction methods that are not implementable using other ways. So we really like neutral atoms. But where is the industry? So the state of quantum. And maybe I should have called this talk a different name. And what I would say is the title of this talk should have been Talk is Cheap. Meaning, for instance, and Michael, I didn't know you were going to be here, so this is for you, right? So you see on one side of the screen, you see, I think, an F-35 bomber, really difficult to build, takes a lot of time. And on the right side, I went into ChatGPT and said, oh, draw me a futuristic plane. That took about 2 minutes, including copying and pasting it into the presentation. So talking about building a quantum computer is easy, or easier. Building it is something else. So we've built them. And customers try to figure out, where are we in this industry? Are we at a point where quantum is now, you could do anything you want with quantum, or quantum is just this futuristic technology that will happen in a few years? And so just to continuing this sort of aviation analogy, we were sort of wondering, let's see if I can make this play. Are we here, sort of in a Wright brothers moment where we're just about to take off?
We are clear for takeoff.
Are we in sort of a DC-3, mid-century, where commercial aviation is starting to happen, or are we in a
Boger, gear is up,
which is kind of where we are, and I'll be flying somewhere tomorrow. So we think that quantum computing has 3 stages, and companies that claim to build large-scale fault-tolerant quantum computers have to show each of these stages I'll show you has sort of 3 checklist items. You don't have to do them in that order, but we have sort of 9 items, 3 stages times 3, that in our opinion are vendor independent and that can be used as sort of a useful yardstick to see how far a company is truly along. Again, talk is cheap, right? So I think the first stage is what we call foundational capabilities. Can you build a qubit? Can you have a stable qubit that remains stable long enough to do some calculations? Is it accurate? Meaning, can you do operations with qubit with a high degree of certainty that the operation is correct? And can it be adaptive? I mean, quantum error correction, the ability to measure qubits to say, hey, it's basically like the quantum equivalent of if-then-else statement. So if this happens, execute this way or the other. So where are we? Well, we do have qubits. In fact, we've got 256 of them on Amazon Bracket for the past 3 years. This is our first computer. It is running online. It's 130 hours a week. So it's not a university experiment that works for 10 minutes on a Thursday. You can take out your credit card. In fact, please do. And you can use it right now, and the cash register will ring at Quera when you do that. And many companies worldwide and HPC centers and scientists have done some really cool things with this computer. So for instance, we worked with Deloitte to do smart defect classification. This is a machine learning application that looked at the end of a production line and tried to classify whether a part is good or bad. We worked with Moody's to do weather forecasting. Moody's serves financial services clients, and they really want to know if a hurricane is just a gust of wind or is something serious. And we work with Amgen and Merck to actually show that with small data sets, quantum machine learning outperforms classical machine learning. Am I claiming quantum advantage? Not really, but this is sort of sparks. This is sort of a harbinger of the things to come. Especially in life sciences, we've done a lot of work with the Wellcome Leap Foundation on antibiotic design and workflows and so on. We're able to tell you a whole lot about these fun activities. So when we look at the foundational capabilities, we think we've checked off 2. We have stable qubits. We've shown that they can do accurate operations. That adaptive, sort of being able to do something in the middle of a circuit, we're working on it. So I would be the first to claim, the first to admit that we're not covering all 9 bases yet. We're working on them, but we have 2 of the 3 here. The second is error correction. This is sort of the DC3 cockpit. So fault-tolerant operation. Can you build a logical qubit? Remember, a logical qubit is a correction of physical qubits that aims to reduce the error rate. And does logical beat physical? Can you get error rates in logical qubits that are better than physical? Can you show that you could actually scale that? When you add more qubits, you get better results. And can you show, in sort of semi-lay person speak, can you show universal logical operations? Meaning, in scientific speak, there are Clifford gates and non-Clifford gates. And basically, you have to be able to show that you can do the more difficult gates, the more difficult operations in quantum, if you want to really take quantum to where it needs to be. Without these non-Clifford gates, a quantum computer could be easily simulated by a classical computer, and so all this work is for nothing. And so we've done that. We have shown what's called magic state distillation, which is sort of that ability to do logical gates and do universal gates. By the way, this is how it looks. I mean, this is a video, of course, slowed down so we can all see it, of atoms moving around. I spoke to you about how we shuttle them, how we bring them together. So this is how an algorithm looks on a neutral atom machine. And we've also shown that because of this movement, we can make algorithms that are much more efficient, that requires fewer cycles to execute. And we've deployed that. So this is a machine that we've deployed in Japan. This is a gate-based machine that ran these magic state operations, logical circuits. And just because I like videos, this is how this machine looks. Right? at least when the doors are open.
That's not upright.
No, I understand. But I mean, like,
This is a live,
what we have on our webpage,
when they weren't looking, I took a video of our machine in Japan. But it's between us, right? Don't tell. And we've been working with government institutions as well. We're doing work with Los Alamos National Labs, both on our first generation machine and on this one. We're doing work with NERSC. We're part of DARPA QBI. So both industrial as well as governmental partners. And so when we look at the second stage, we actually think we've demonstrated all of them, that logical qubits beat physical, that fault tolerant, we can show how we scale, and that we've done these universal operations. So I think we're actually in pretty good shape. And when you look at the third stage, that's the sort of mass quantum advantage. You know, can you actually show that you can do something on a quantum computer that is either faster or cheaper or more accurate than a classical machine? Can you have production grade? Again, meaning, does it run only for 2 minutes in the university setting, or can it run 130 hours on the cloud where anyone can use it, adhering to strict service level agreements? And is it deployable? I mean, we've seen vendors who say, yeah, we can build, one day we will build a 1 million qubit computer and it'll be really good, and it will take a size of a football field, it'll cost $1 billion, and it will require 100 megawatts of power. And that may be great, but it's still a football field and $1 billion and 100 megawatts of power. So towards that goal, we are building supercomputers with NVIDIA. This is what you see here. It's maybe a little bit hard to see, is one of the most famous people in the world shaking hands with Jensen, the CEO of NVIDIA. No, this is Misha Lukin, a scientific co-founder of Quera. We are working with NVIDIA on the NVAQC and Advanced Computing Center in Boston, and we're looking to both explore how quantum helps AI and how AI helps quantum. So when we go into all of these, we haven't yet shown quantum advantage. Again, just to be completely honest, we have shown production grade, and we are showing that our systems are deployable. In fact, we deploy them. And so when you look at other quantum vendors, and by the way, this checklist is available both online as well as in our booth. Just pick it up. It doesn't say neutral atoms, doesn't talk about any specific modality. We think it's just an objective way to think about progress. But when you talk to vendors, just ask them, you know, which parts of your roadmap, talk is cheap, right? Anyone can create a PowerPoint and say, I'll create a supercomputer by 2030. But which parts of it have you actually shown? Have you deployed any systems on the cloud or on premises? Will it be, how large will it be? How much energy and how much will it cost? And just to conclude, or almost conclude with the airline analogy, or the airplane analogy, on the right, you see the B-2 bomber. 22 of these were made. 70, I think, were ordered. 22 were made because they cost $2 billion each. On the left side, you see a 777. I think close to 2,000 were made and are still being made. So our goal is really to build the 777 of quantum computing. We think it's going to be super useful. We think it's going to be affordable, so that a mid-sized university and certainly most of the Fortune 500 will both can afford it as well as want to afford it. And this is where we're heading, and I think we're getting very close to that point. And just in summary, how can you engage with us? Well, you can work with us on quantum systems, which you can either buy or use on the cloud. We do a lot of collaborative research, just like we're doing with Los Alamos National Labs, just like we're doing with pharma companies or energy companies. And we're also doing application code design, where we work with customers to say, let's find a problem that we think can work well on our quantum computer, and let's optimize it to take advantage of the special capabilities that we have. So with that, we think we are showing a practical path to quantum computing, and I'd be very happy to continue to talk to you offline about what we can do for you. Thank you very much.